I'm not going to go into a lot of detail, but basically what I had to skip, and it's maybe not a good thing I skip it, but another important concept is electrical fields. Okay, so an electrical field, so let me start by that. An electrical field is a field where a positive charge will experience a non-contact force, a non-contact force. So, and if that force is big enough, it will cause a positive charge. Now, what is a positive charge? It's a proton, for example. So, for example, the hydrogen anion is a positive charge, or it's something that's given away its electrons. So it's not necessarily that, but it's something that's given away electrons, and now it is positively charged, and so it is experiencing a force. Now, the only way for a positive charge to experience a non-contact force is if there is a negative charge nearby, or a positive charge nearby, because positive charges will repel other positive charges, negative charges will repel other negative charges. So imagine I have something here, an object, and this object, and this is actually not motors and generators at all, but I do think this is quite important, and this object has given away electrons. So I don't know how many electrons, but it's given away some electrons. That gives it a positive charge, and we represent charge with a Q. Okay. Now, if you had to go and work out what that charge would be, charge is measured in Coulomb, then you would literally go and count how many electrons did he give away. Because every electron that he gave away gave him a positive Coulomb charge. So, for example, if he gave away one electron, okay, then we'll go to our periodic table, and then we see, well, if an electron has a negative 1.6 times 10 to the power of 19 charge, then now this thing has a positive 1. It's, in other words, charge is almost a measure of how many electrons or lack of electrons do you have. Okay, so then we'll subtract. It will have that. If I gave away 2, I'll just multiply this with 2. If I gave away 8, then I'll just give this an 8. So this one will have a charge. So if I have what is called a unit charge here, so I'm just going to represent a unit charge, means it is a positive something that has given away 1 Coulomb of electron. No, is it 1 electron? I think it's 1 electron. And so he has that charge, but in positive. So this is a unit charge. He's given away 1 electron. So this thing has a positive charge. Now, what will he experience from this positive? This positive charge will repel him. So let's do it like this. So we've got our charge here, Q plus, and here's Q, and this charge will repel him. Okay, it will push him away. Now, if I put this Q wherever around, it will repel him like that. And so if I had to draw what is called field lines would just represent is if anywhere here I would put a positive charge, it will push it away. So the field lines around a positively charged object will look like that. Okay, because at any point a positive charge will just be pushed in that direction, directly perpendicular to the tangent at that point. Okay, so now a negative one, if this thing had a negative charge, it would have the exact same field lines, but they will just be pointing towards, because he will pull them in. Does that make sense? So it's all about what will happen to a positive charge. Now imagine I have two charges, one charge here, it's a positive charge, and one charge here, that's a negative charge. Now imagine I put a positive charge here in the middle. What will happen? Well, this one will push him away and this one will attract him. Okay, so here it's very important to actually know where the center of this, the middle line between these two, or the symmetry line between these two are, because that's going to help us to draw the lines. And you'll see the first one right in the middle is not difficult, because this one goes away from there. Okay, while if I put a charge somewhere here, for example, a little bit close to him, we would expect him to be pushed away in this direction. He gets pushed away in that direction, but this one pulls him in towards him. Okay, so but the pull is not as strong as the push, because he's closer to this charge, assuming these two charges are equal. So the push is stronger than the pull, but it's not 100% away in the original direction, in that direction. It's slightly curved towards it until it comes here in the middle. Once it reaches the middle, now the push and pull is equal, so now he will go horizontal. But the moment he goes horizontal, now he's coming closer to this one, so now this one will start pulling him in. This one is still pushing him out, so that the overall pattern, if we had to do it continuously, makes these curved lines. Okay, so here we start from there, we start just moving away perpendicularly from that surface. So we start moving, but as soon as I do that, I start turning. Once I get to the middle, it's horizontal, and then I should, from this side again, aim to meet it perpendicular. Okay, same here. Initially, I will move away, but then this thing pulls me in its direction if it's strong enough. Okay, but probably it's not, so it will just at some point go off in that direction. And if there was something here, it will just pull it towards here. Likely, it's possible that they can, it just depends on how strong these are. The stronger they are, the more these graphs can curve. Okay, but weak ones will quickly, instead of he will just get away, because at that point this one can't maybe affect him enough. Okay, but as soon as I pass this side, okay, it will move away, but they'll just have a slight pull towards there. So on this side it will look similar as soon as I pass this horizontal distance. On the other side, however, on this side, this one is pushing him away while this one is pulling him back, but obviously this one is pushing away harder than that one can pull back, so the charge will move in that direction. Okay, the same on this side. This one is pushing him away, but this one is pulling him, and since he's closer, he's going to pull him stronger. So the net effect will be that he will go in that direction. And then this side down here will just be a mirror reflection of that side, so I'm not going to draw it. Okay, now if they were two charges that look the same, so I had a positive and a positive charge, then again I need this middle line. And if something lies on that middle line, notice this one is pushing him away and that one is pushing him away, and imagine both of them are the same size. Then this push that they have towards each other would cancel each other out. So two people that can push with the same strength on something that's between them, it won't move at all. So there won't be any lines here. The moment I'm come this side, I'm closer to this one, so he will start pushing away, but just until I get there, and then it will start pushing back. So along the center, there's no lines along the center. I can't go forward or backwards, because when do I stop drawing? If I draw an arrow, it means it continues, but it doesn't. So there's no where am I at? Okay, don't know what I did, but it's back. Okay, so along the center, there's no lines. So I'll go to the next one, the one that's kind of, if this is north. Well, let's start with north. Yeah, let's look at what will happen to this one. This one, originally he will be heading away at about a 45-degree angle, but as he's going in this side, this one is also pushing him away. Okay, so he's not just experiencing a force in this direction, he's also experiencing a small force in that direction. So what will end up happening is he will end up curving, but he will never reach this line, to the hyperbola shape. So if I had any field lines between this one and this middle one, he will do the same, but he will just curve more. And very important, they will never cut each other. Field lines can never cut each other. Okay, and then the one that's up here, he will want to go up, but this one experiences slight force on it, so he will just curve slightly away because of that one's effect at some point, and then he will just end up going in that direction. So the one in between here, exactly the same, will just have slightly more curvature. The one here, again, now he's getting away a bit more, further away from this point, so this point's effect is not that strong on him. On this side, it would just, both of them are pushing him away, so it's away. Okay, again, the bottom side is just a mirror image of that side, and this side will look exactly the same. As I go along here, middle, that one starts pushing him away or starts having a greater effect. Any lines that I draw in between will look similar, they'll just curve a little bit more, but they'll never cut, and the rest will look exactly the same. Okay, you get that? You know how to draw this. You're fairly okay with it. Just want to show you if they now were, so we've done same charges, if this was negative, it would just be in the opposite direction. Okay, they would just be towards if both of them were negative. I just want to show you now one more. What if one was a small charge and the other one was a big charge? The difference is now going to be, so imagine this colored one is a big charge and they're the same charges. We'll assume they're the same charges. If this one is a big charge, okay, it means that the effect where they start cancelling one another out only happens further away from this one, closer to where this one's strength is more comparable to that one. And the reason why is, and I should have maybe started with that, is that the force that that charged particle experiences is directly proportionate to the charge of the particle that's having an effect, and the distance between the particle that I'm talking about now, this Q that's somewhere here, squared, multiplied by a constant. Now this constant is called, I think it's Coulomb's constant, okay, which is on your formula sheet. There he is, Coulomb's constant, yeah. Okay. Okay, so in other words, when will the force cancel one another out is when, I said it's same charges, let's make them opposite charges. This one positive, for example, and that one negative, but this one's still the strong charge. So So the attractive force and the repulsive force, where will that be the same? Well, it will be further away from the stronger one and closer to this one, because the further away I go, the smaller the force becomes because of R that's being divided. So it would be roughly somewhere here. Depending on how strong that one is, the stronger it is, the closer it is to the weaker one. Okay, but it won't be in the middle. Now, this just helps me give me my shape, because I still do the same shape. I go away from positive and towards negative, so this line still looks the same. But what happens to this line is, remember, at this point he must have a horizontal gradient. So if I had to draw him here, it will look like this. Okay, notice that this bulge here in the middle appears a little bit more towards this side. Okay, and then the further they are away, you can end up seeing that at some point, even here, it's still strong enough to pull it all the way towards it, while some of these might now tend away because it's no, towards. Okay, because it's strong enough. While at this point, this one will push him away and this one will pull him, but obviously not with enough force to pull the whole thing, because then it will pull this thing. Okay, and the bottom will still look the same. Okay, if it was in the same charges, I'm not going to look at that, but again, the same thing. It's like this, but now your asymptote, that line that they never reach, is more towards this side. So the stronger ones, lines are more accented. So they're bigger, they further away, while the smaller ones are more squeezed in together. Okay, here as well, you see how they curve quicker, while the bigger one is more accentuated. That's the word I was looking for. Okay, now this was important for various reasons. Let me just quickly see at the exam question so that I at least mention the topics to go and look at the charges. Now, field strength is now defined as the amount of force that a particle will experience at that point. So if I have a charge Q here, and I have another a unit charge here, okay, how much force will he experience at that point? Now I can see it then depends on how far it is away from the charge. So sorry, I made a mistake here. Force is the charge of the one charged particle times the charge of another charged particle, okay, multiplied. So the stronger these two are, the stronger the force is that they exert on each other. Field strength is the force per unit charge. So it's literally asking one of these two is therefore Q. Okay, one of these two. So in other words, field strength, and you'll see it's is given by this, so it's KQ over R squared, and that's the amount of force experienced per unit charge. And that's why when you look at the formula, it's not here, but it is charge per is it still charge per Newton per charge? Newton per charge. Okay. Nevertheless, you can still see that it does depend, the field strength does depend on how far I am away from the charge, but also how strong the charge is. But what happens now in these cases is, now if I put a unit charge anywhere here, it is not just one, I'm not just experiencing one force. I'm experiencing a force in this direction and experiencing a force in that direction, so I'm experiencing a net force in this direction in a sense. Okay, so if we just had two charges, Q1 and Q2, since I have two charges, I now have a net field depending on where I am. Okay, so depending on where I am, I'm going to have a net field, and it also depends on what the two charges are. So for example, if you had to calculate the net field strength, you will look at, well, at what point, where are they saying I'm calculating it from? Let's say I have to calculate it from here. The next question that I'm going to ask, well, how are the two, I've got two things having an effect on that. So I'm going to need this distance, let's call that R1, and I'm going to need that distance, R2. Now it's going to depend on, well, what are the two doing? Are both of them attracting me? Are both of them repelling me? Now it depends on the charges. Okay, so at this point, if both of the charges are positive, what will happen to a positive charge? He will be pushed away by this one, and he will be pushed away by that one. Are the two charges working with each other or against each other? With each other. Therefore, the net field line would be the net field of one plus the net field of the other one. Okay? If one of them was positive and one of them was negative, then this one is pushing him away, this one is attracting them, so they're working against each other. In other words, whatever this one is pushing away with, this one is attracting with. Now it's going to depend who wins. If this one is big enough, he can, despite this one being closer, if this one's charge is large enough, he can end up pulling him in this direction. Okay, that's if they were different. But notice that if they were different and I'm outside of the two, then they are working against each other. If I were in between the two, okay, and they were the same, this one is pushing me away and this one is pushing me away. So are they working with each other or against each other? Against, because this one is pushing me away in his direction and this one is pushing away in against that. So in other words, you literally have to go and look what is happening. One is going left, the other one is going right. In other words, the net field is the difference between the two. Does that make sense? Now, if the one was positive and the other one was negative, okay, and it was outside, then I would use the difference. But if I'm inside the two, then the one is pushing me away, the other one is attracting me. The one pushing me away is pushing me in the direction the other one is attracting me to. So now they're working together. So the net field lines, or the net field, is the one plus the other one. Okay. And again, it is very important to go and find the distance from where my point is to where I'm going. So just with that, I just wanted to say enough so that we can actually just answer this question. But it's also, guys, this is not a difficult topic, not at all. Okay. The first one states Coulomb's law in words. Coulomb's law is just saying that a positive particle, or the force experienced by two charges. It's literally looking at that. So look here. Coulomb's Coulomb's law is literally looking at this formula and saying the force experienced, the force between two charged particles is directly proportionate to the charges on each particle and inversely proportionate to the distance between them squared, or the square distance between them. So literally just stating that expression in words. Okay, same with Newton's second law, for example. Acceleration, and so you just take this, that when there exists a net force, the acceleration is directly proportionate to the net force and divided by mass, inversely proportionate to mass. Okay. Yeah, draw the electrical field pattern due to these two charges. Okay, so there's the two charges. Notice that the one is double the other one. Okay, which means that that center line is not in the center. We must move it. So we'll move it away from the strong one, so probably about halfway away. Okay, so roughly here at P about anyways. So the field lines will take these bulges. The bulge will appear earlier rather than in the middle, and it will go from positive to negative. So for the 3 marks you got is one getting marks for actually drawing the field lines going from positive to negative, and the fact so that's the 1 mark. The other mark is that the field lines meet each other, because if it was same charges, the two field lines will never meet each other. And the last mark goes for having that correct bulge, having the correct shape. Okay. Calculate the net electric field at point P, situated, so they want it. And strangely enough, very few people actually got this correct. So, and again, it's not, you can get full marks for this question. The net electric field is then one of these two. It's either the sum or it's the difference between the two charges. I've got two charges. Now I must just know if it's the sum or difference. P is a unit charge, they tell me. Point P. Okay, if P is just a point and they ask me what's the field line, they're asking what will happen to a positive charge. Okay, so the positive charge would be attracted to Q1 and repelled by, so Q1's effect is pushing it in which direction? Towards it. Q2 will have what effect? Pushing away, but let's compare it to what the original one. If you said the original one that it was pushing it towards Q1, now ask what is Q doing in terms of, is it also pushing it towards Q1 or away from Q1? Towards Q1. So are they working together or against each other? Together. Both of them are pushing him towards Q1. You understand? So now, would this be a positive or negative? Positive, because they're working together. The field strength is being, the one is adding to the field line of the other one, or the field strength of the other one. And then this is literally just Q1 divided by R, the distance between point P and Q1 squared, plus Q2 divided by the distance between point P and Q2. And K is a constant, 9, I think 10 to the power of 19. No, 10 to the power of 9. There is K. Okay. So 9 times 10 to the power of 9 times Q1. This was important. This threw some people off. Nano. Where am I? Oh, back. Nano Coulomb. You can't use -7. We work in coulombs. So nano Coulomb is 10 to the power of -9. Yeah. So this is times And here, because we've already considered our sign in a sense, we shouldn't use the -7. Okay, don't use the -7. You just use the positive, because we've already considered what the signs are going to do. Okay, times 10 to the power of -9. Because if you're going to consider the negative, it's going to make this one negative, that one positive, and they'll again be two different signs.
I'm just thinking about it.
Okay, are you sure? So you understand what I just said?
Yeah.
Okay. And now the distance between Q1 and point P, that was important. You got a mark specifically for that, because this distance between the two is 2.5. So, and the distance between these two, so how would you find the distance between P and Q1? From 15 to 24 is 9, so in this case the distance is 0,9 squared. Plus, and now the other one is 9 times 10 to the power of 9 times 15 times 10 to the power of -9, all over, and this distance was 2,4 squared. And it's now just notice again, I've already considered what the positive and the negative do, and I just find it easier to do it that way. And in the end, whatever answer you get, remember this is a vector value, so it's Newton per Coulomb towards Q1. So you would lose a mark if you don't put that, because it's a vector quantity. We have to give our direction. Okay, so there you can definitely see it's not difficult, and they seldom make it. It is possible to make it more difficult than that, but this is a very common question. You can get 10 marks for that. So these last questions in your paper 1 are really, except for the electricity. Electricity can get slightly complicated, not really, but slightly. While all of the others are really very simple. If even photoelectric effect, they're not difficult concepts. They're usually theoretical, and there's not a lot of theory, which is nice. So I would even recommend that you start with some of these questions. Just get them out of the way, and if you don't remember some answers, go on with the question. You'll probably have some time in the end to think of them a bit. Okay, so let's quickly get to motors and generators that I also wanted to get to. And then in tomorrow's Pretoria lesson, I'll do the photoelectric effect and electrochemistry.